In this example, we will be analyzing an interesting situation called hydroplaning of a car when the car brakes on a very wet road, and because on a wet road there is a thin film of water between the tires and the road, the vehicle basically slides uh, until some distance before it comes to a stop, and that is basically called the hydroplaning of the car. And that happens because this thin film is made up of water, which is a liquid, and so that the friction is basically reduced. Uh, so in this problem, we want to analyze uh, how the vehicle will move, how much distance it will travel before coming to a stop. And while solving this problem, we will utilize some assumptions so that life becomes simpler and it is easier to solve this problem. And we will be using basic concepts of viscosity and shear stress that we learned in our class. So with that, let's get started with the solution. I will quickly draw a basic sketch of the situation. Let's say this is the road on which the car is moving. This is the car. These are the wheels. And there is a, obviously this sketch is exaggerated, but there is a thin film between the tire and the road, and the thickness of this film is given by H. And we are also given the water viscosity, which is mu, and the combined area of all the four tires is A. And this car is moving with velocity v, let's say, in the forward direction, and the mass of the car is capital M. So how would one find out the force which is slowing down the vehicle? Now, if you look carefully, the only force that is acting on this car is due to the viscous shear stresses in these thin films here. And if we can evaluate those shear stresses in terms of the vehicles given here, we would be able to find out the force. Now, so let's see what is the expression of that force. So from your classes on viscosity and shear stresses, you know that the shear stress depends on the viscosity and and the velocity gradient du by dy. So let's just introduce a coordinate system here. Let's say this is my x direction, the vertical direction is y, and if you zoom in this thin film, what you will find out is you have a road, and this is the upper plate, this is the tire surface, and this is the road, and this tire surface is moving forward with the same velocity as that of the car, let's say v, and this road is stationary. So from the no slip boundary condition, we know that the water near the tire surface will move with a velocity of v, while the water near the road will not move as the road is stationary. So this is like a flow between two parallel plates, and since the thickness h is very small, compared to, let's say, unit length, we can assume that the velocity profile between the tire and the road is linear. So we will assume a linear velocity profile, which is a very good assumption because the film thickness h is very small. So this by the choice of our coordinate system, the shear stress will be tau yx, and it will be given by mu times the velocity gradient du by dy. So the velocity here is a function of y. So since the velocity profile is linear, the velocity profile is given as v times y by small h. So it is 0 when we are close to the road, and it is v when we are close to the tire surface. So from this, you can find out the derivative of the velocity du by dy is simply v divided by h. Now if you substitute this in the shear stress, you'll get tau yx will be equal to mu times v divided by h. But remember, this is the shear stress due to the road on the water, or since we have a linear profile, the velocity gradient is the same everywhere. Uh, so this is also the shear stress due to the tire on the water film. So if you zoom in near the tire and look at a small fluid element like this. So our con convention for the stress tells us that a positive shear stress acting on this fluid element is directed as shown by these arrows. So so the shear stress acting on the tire due to the fluid, which is water in this case, will be in the opposite direction like this, and this is the tau yx on tires due to the fluid. So this stress is acting in the opposite direction on the tire. So this because of that, this force is basically opposing the forward motion of the vehicle, and we can evaluate it just multiplying the stress by the area. So so the force F on the car is nothing but tau yx multiplied by the area of all the four tires, which is given to be A in the question. And and because this force acts in the negative direction, we will introduce a negative sign. So F is basically minus mu times V divided by H multiplied by A. So this is the answer to part A, where we found out the expression for the force in terms of A, V, H, and mu, which is trying to slow down the vehicle. And this the origin of this force is basically the shear stress in this small film of water between the tires and the road. Now in the second part B, we are asked to find the distance L that the vehicle would slide before coming to rest. And A and H are assumed to be constant, which is again not realistic as the vehicle will slow down, the area and the height might change, but just to simplify the analysis, we will assume them to be constant. So part B, we want to find out the distance L that the car would travel before stopping. So for this, we will make use of Newton's second law, which is force is equal to mass times the acceleration, and acceleration is basically the time derivative of the car velocity, dv by dt. So we already found out the expression for F in part A, which is here. We just need to substitute the expression for force in this equation and solve. So mass times acceleration is equal to force, which is minus mu v a by h. So simplifying, we get dv by dt is equal to minus mu times a divided by h times m into v. So this is an ordinary differential equation in terms of v, and we just need to integrate to find out the v. So dv divided by v is equal to integrating on both sides mu times a divided by h times m dt, and the limits of integration are, let's say, 0 to t and some initial velocity v naught to a velocity v at time t. So and this is just a constant because mu a, h, and m are all constants. So if you solve, you will find out that it is natural logarithm of v divided by v naught is equal to minus mu times a divided by h times m into t. So writing v in terms of v naught, you will get v is equal to v naught times exponential minus mu a h times the mass t. So this is the expression for velocity in terms of time. And now when the car stops, we will have v equal to 0. And now since we have the expression of velocity, velocity is nothing but the time derivative of distance, which is equal to v naught times exponential minus mu a t divided by h times m. We can, again, this is ODE for x, which is the distance the car travels. So if we integrate it, dx from 0 to x is basically equal to v naught times integration 0 to t, this term in the exponential, dt. So solving this, you will get x to be equal to m h v naught by mu times a 1 minus exponential minus mu a p by h times mass. Now the car will stop as time goes to uh, time goes to a very large value. So eventually the car will stop. So we will basically use this limit, time going to infinity, in the above equation. X will approach the stopping distance s in that case. So L is basically limit t tending to infinity in the expression of x of t, which is this. And if you substitute it, you will find out that L is equal to mh v naught by mu a. So this is the stopping distance for the car in terms of its mass, the film thickness s, its initial velocity v naught, the viscosity of water, and the area of the tires. So this is the answer to part B, which is the stopping distance L as the vehicle hydroplanes. Now in part C, we are just asked to find this distance as L for the given mass of the vehicle and the area of the tires given, and and film thickness and the initial velocity is also given. So we just need to substitute all these values in the expression that we just found out for the stopping distance L. And if you just substitute all of those, you get 1000 kg mass. H is point point 0.1 millimeters, which is zero point 0.1 times 10 power minus 3 meter. V naught is given to be 10 meter per second divided by the water viscosity is given 0.001 kg per meter second, and the area is also given, it is 0.1 meter square. So if you solve this, you will eventually find out that L is 10,000 meters, that is 10 kilometers, or it is closely equal to 6.2 miles. So basically using these approximate values, you will find out that the vehicle will travel almost 6 miles before coming to stopping completely. And again, this is not realistic. 6.2 is a huge huge distance. So that's just because our assumptions that the film thickness h and the area of the tire A remains constant is not a very good assumption. And as the vehicle, as we apply the brakes, they change such that this distance L is very small. Yes, so that's how you solve this problem. So basically to find out the force that is decelerating the vehicle is nothing but the shear viscous shear acting on the tires due to the gradient in the velocity in these small fluid films, and the shear stress then depends on the viscosity times the velocity gradient, and if we just multiply the shear stress by the area, we find out the force that is trying to slow down the car. And then we used Newton's second law to relate the force to the acceleration, which is nothing but the time derivative of velocity. We found out the expression for the velocity, how it varies with time, and again we use the fact that velocity is just the time derivative of the position x in this case, and we again solved this ODE for x and found out how the distance varies with time, and as the vehicle stop, which it stops eventually, so we used the limit time tending to infinity and found out that the stopping distance L turns out to be mass times the film thickness times the initial velocity divided by the water viscosity times the area of the tires, and we just substituted the given values to find the solution to part C.